Hey, welcome to the Electronics Lab. In this video, I'm going to talk about parallel devices and parallel circuits. So devices are in parallel when they share a node on both sides of the device. So these two resistors are in parallel because they have a node that they share in common at the top and a node that they share in common at the bottom. So another way to say that is that these two devices share common electrical points on both sides of the device. Now, it doesn't have to be resistors in the circuit. It could be diodes, it could be capacitors, it could be inductors, as long as those devices are sharing a common point on both sides of the device. And because these devices share a common point, the voltage across them is going to be the same. So the voltage across this resistor and the voltage across this resistor are equal to each other. I'm going to redraw the circuit. Give me a sec here. Now, the voltage across these devices may be the same, but what about the current? Well, the current through the devices is not necessarily the same. And we can use an analogy to help us think of this. So you can imagine we have a pipe with water flowing into it. Now, if this pipe came to a branch, we'll have some amount of water flowing in the pipe here, and then that water gets split amongst those branches. And whatever's, let's call this flow 1 and flow 2. And the amount that's flowing through pipe number 1 here, plus the amount that's flowing in pipe number 2, has to equal this initial flow. However, flow 1 and flow 2 don't have to be equal to each other. And then if they join back together, what we have coming out there will be the initial flow. So this is analogous to what happens in a circuit when we think of current flow versus water flow, or current flow compared to water flow. The current that's flowing, the total current, let's call this IT, that's flowing in the circuit, when it comes to a branch like that, it's going to split. And let's call this I1, and this is I2. The total current that's in I1 plus the current that's in I2 has to add up to that total current. So this current's flowing into the branch. Some of it goes this way, some of it goes this way. It's not necessarily equal amounts that goes through those two paths. Then they come back to join together in this node, and it's going to be the same total current that's coming out of the node. So this is a brief introduction to Kirchoff's current law. And what Kirchoff's current law says is that the sum of all of the currents that are coming into a node has to equal the sum of all of the currents that are leaving the node. In this simple example here on this node, I've got one current coming in and two currents coming out. I1 and I2 have to add up to equal I total. I wanted you to know about this because I want to take a look at a situation where we have a voltage source connected to a whole bunch of resistors in parallel with each other. What we want to do here is figure out what is the equivalent resistance that this voltage source sees when we have all of these resistors in parallel with each other. Now let's say we've got R1, we've got R2, we have some number of resistors here, and we've got Rn. So it could be any arbitrary number of resistors. So what are some things that we know about this circuit? Well, we know that since all of these resistors are in parallel, the voltages are all going to be equal. So the voltage source is going to be equal to the voltage across R1, it's going to be equal to the voltage across R2, and voltage across Rn. Of course, also equal to all the voltages in between. What else do we know? Well, we know from Kirchoff's current law that if we call this IT, and each one of these is the current associated with the resistor, so IR1, IR2, IRN, we know that the total current coming into that node has to equal the total current coming out of the node. So that's going to have to be IR1 plus IR2 plus all of those other currents plus IRN. What else do we know? Well, we know that current in general is equal to voltage over resistance. So we can take that equation for each one of these branches and say IT is equal to V over RT. And that's going to be equal to V over R1 plus V over R2 plus all of those other currents in the form of V over the resistor plus V over Rn. And those V's are all equal because all those resistors are in parallel. So those will all cancel out. And what we end up with is 1 over RT. So 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over all those other resistors plus 1 over Rn. So what we have is the total voltage that this voltage source sees is going to be equal to the inverse of the sum of the inverses of all of those resistors. So that equation right there. So in summary, what have we learned about parallel devices and parallel circuits? Devices are in parallel when each side of the devices share a common electrical point, like these ones do. We also learned that Kirchoff's current law says that the current going into a node has to be equal to the current coming out of the node. And finally, we learned the equation for the equivalent resistance when we have resistors in parallel. And that's it. Thanks so much for watching. See you soon.